Let me show you how to be a good breezy and change your predictions after.
Okay, hi everybody. So welcome to the very first Learn Bayes Stats modeling webinar. I am super excited for this one. And we have a great guest to begin with because Samir Deshpande is with us today. So you may already know him from episode 80, where we already talked a bit about BART and your work, Samir, about all this stuff. But I'm going to let you introduce yourself quickly, and then I think we'll jump right in. So Samir, can you tell us a bit about yourself, knowing that if you guys want some background story about Samir and all that stuff, go back to episode 80. We talked about that in depth, but yeah, just a quick introduction, Samir.
Yeah, so hi everybody. It's very excited to be here. So I'm Samir Deshpande. I'm an assistant professor at the University of Wisconsin-Madison, and I work primarily on Bayesian methods. And most recently, I've been working a lot on Bayesian tree regression or with BART. And I'm also interested in things like hierarchical modeling and spike and slab variable selection and various other things. But today, I guess we'll be talking mostly about BART.
I guess, yeah, although it depends on the questions from people.
Sure.
So let me actually address that kind of the infrastructure of the workshop, and then I'll let you the floor, Samir. So yeah, several things, people. A common question, yes, this will be recorded, and you will get access to the recording because you are here. So of course. Second, Samir will go through the code and the analysis by sharing his screen, but Christophe Banberg and myself are there in the background to ask any of your questions. So if you have any question at any point, please post them in the chat. And I think that it's the first time I use Riverside for this kind of event, but I think as a member of the audience, you can ask to be called in the recording to ask us your question live. So if you feel like it, you are welcome to ask for that, and then I will personally welcome you to the call, and you can talk a bit with Samir. On that note, again, use the chat for any troubles or else. There is some background noise coming from Samir, as you can hear, but it's coming from the AC. There is not a lot we can do about that. Hopefully, it will not be too strong for you right now, and it should be better in the recording. So yeah, basically, I will give it up to you now, Samir, and thanks again.
Thank you again, and I'm excited. So what I've done is I've prepared a couple of examples. Some using some real data or a subset thereof, and some using synthetic data. And what I thought I would do is kind of show how BART is used kind of out of the box using one of the kind of more popular implementations. And then as a bit of shameless self-promotion, I'll show some examples with the new implementation that does a few new things. And you know, live coding is always kind of hit or miss. I might say something or go quickly, or if I scroll on my screen too fast, just stop me, and I'll make sure that all of this gets posted as like an R Markdown somewhere on my GitHub, and we can talk about sharing that link, or it'll be as like a vignette for a package. So there'll be all the gory details will be made available, but please don't hesitate to stop me as we're going through this. So let me share this window. And let me make sure I get the right one. So I think you should see a RStudio window. Is that the case?
Yes, we can see everything, and that's actually a good level of zooming, so perfect.
Thanks okay. I'll go just a little bit bigger because it'll make it easier for me. So the first thing that I want to do is talk about maybe the prototypical example of BART and BART, right, is about estimating a function using a sum of regression trees. And formally, it's Bayesian. We put a prior over these regression trees. We update them to get a posterior. Now, a distribution over the set of trees is extremely complicated. It's totally intractable. And so we have to use some sort of MCMC to do any of our posterior inference. And so one of the first examples that's in the original BART paper to show just sort of how powerful this idea of approximating functions using trees is to use what's known as the Friedman function. So I'm going to copy a link into the chat for the Friedman function. This is a function that is based on, I think, 5 different variables, and it's nonlinear. And so what I have in this first bit of code is I'll just kind of write my own version of the Friedman function. You'll read in some x variables, and in this case, we'll need 5 of them. And it's the function has like some sort of sinusoid of x1 times x2. It has a quadratic term in x3. It has linear terms in x4 and x5. So this, right, can't be well modeled with like a linear model or even a like quadratic expansion or like a polynomial basis. This really is kind of a complicated function. And so what we'll do is we'll just set up our R session to have the Friedman function in the background. And what we'll do now is demonstrate how to use BART to estimate this. So specifically what we're going to do is we're going to generate some data, let's say 10,000 data points, and we're going to draw a bunch of covariates. So in this case, we'll draw 10 covariates. So the first 5 are relevant, the last 5 are irrelevant. And for simplicity, we'll keep these covariates scaled to like a unit interval, say -1 to 1. And what we're going to do is we're going to take these x's and we're going to evaluate the Friedman function, and then we're going to add a bit of normal noise to get our outcomes. And once we do that, we will pass that noisy versions of the Friedman function, the outputs, and our inputs x, and we'll pass them into BART. And we're going to be interested in 2 things. The first is how well can we evaluate this function, this unknown regression function, on the training inputs, and how well can we approximate it out of sample? That is, if we give ourselves some new x's or some testing x's, how well can we predict the Friedman function out of sample? And so what I'll do here is I'll just kind of set things up. So I'll define 10,000 training observations. I will set aside maybe 1,000 testing observations. I will use 10 covariates. I'll generate a matrix of these covariates. I will create some testing covariates, and then I will evaluate the Friedman function and add some noise. So here I'm adding noise with normal noise, mean 0, variance 1. Nothing too complicated, and so we'll run that. This is all by way of just setting up some data. And the other thing I'm going to do is I'm going to compare 2 implementations of BART. One is the BART package, or BART. That is kind of, I think, the canonical go-to package. Whenever I need BART in sort of applied work, that's the one I tended to use. And then I'll also try a new implementation that's kicking around in a package that we call FlexBART for a more kind of flexible version of BART. So what I'm going to do is, after I've defined this data, I will create a couple of containers to store, say, the out-of-sample root mean squared error for both versions of both implementations, and also keep something for the timing. BART is a relatively fast algorithm, but we'll kind of see how fast really is. So this is all by way of getting set up. And one of the nice things about BART is that it almost works unreasonably well for what it is. Unlike a lot of machine learning methods, you really don't need to fine-tune hyperparameters. We're doing regression, but we don't have to specify functional forms. And in reality, it is about as easy as arranging your x's, arranging your y's in sort of the right vector, putting your x's in a matrix or a data frame, and calling a BART function. So it's in some sense as easy as doing something like BART xy. Now, that's being a little glib. In fact, to use the BART package you want to end up using the function WBART. That is the BART implementation for regression with continuous outcomes. And what you have to specify at least two arguments. The first argument is your training x's, just your design matrix or a data frame of all of the x's. You need to specify your output, your actual observations, and then optionally you can specify a data frame or a matrix of your test set inputs, the points you want to make predictions at. And that usually is enough, but there are some built-in arguments that are, if you look at the help file, it's mostly things around how many MCMC iterations you want to do. Do you want to do any thinning? Do you want to save your samples? Do you want to save samples of the trees? A lot of them are passed by default, and there's usually not a real strong reason to change any of them, other than changing the number of MCMC iterates. So out of the box, BART will run a single chain of MCMC. I believe the default is about 100 burn-in samples and 1,000 sort of post-burn-in samples or post-warm-up samples. I kind of like to use 1,000 for each. That kind of old idea of burn in half your chain, but things tend to stabilize. So before I proceed, I will say that this is kind of the plain vanilla version of BART. It is regression trees that have constants at the leaf nodes. I see there's a question in the chat about allowing linear models on the leaf. To my knowledge, the BART package doesn't support this. To put a linear model at the bottom of the leaf, I believe there is some work that's come out in recent years, but I don't remember what the name of that package is off the top of my head. So it exists, but it's sort of something that people have had to roll on their own. And maybe we can talk later on about this. So what I'm going to do in this bit of code here is I'm going to run BART using sort of the out-of-the-box sampler. I'll make it do 2,000 MCMC iterations. I will then compute kind of the root mean squared error on predicting that regression function in sample and out of sample. And as kind of suggested by this code, the way that I'll do that is I'll save the output of WBART into an object. I guess I called it BART fit. And that thing is going to have a bunch of named attributes. So I'll run this, and then we'll investigate those attributes. And I'll apologize now that we're going to hit the moment where you're going to have to watch my computer do some MCMC. And maybe as we're waiting for it to run, we can address this question here in the chat. So let's get this running. And you'll notice that WBART spits out a ton of things to the console. A lot of it is stuff that you can safely ignore. So the question of, what would the benefit of having a linear model at the bottom of your trees do? It makes things more flexible, right? Without, better extrapolation, maybe, but you'll get smoother fits. In some sense, BART is estimating a function with piecewise constant step functions. Putting a linear model there is now allowing you to do piecewise linear. So I imagine for certain functions that are reasonably well approximated by piecewise linear things, maybe a convex function or kind of these polyhedral functions, they'll probably look really good. You may be able to use fewer trees. There's a paper on this where I think they found they could use fewer trees and sort of a smaller number of parameters by having linear models at the bottom of a BART. And yeah, I think it's a good idea. I just don't think that those are currently supported.
I have several questions about that. That would be first, what kind of MCMC is that running in the background? Is that using nuts or is that another one?
This is all Gibbs sampling.
This is Gibbs sampling. Okay.
Right, and this is important to note because tree space. What you're doing is you've got a collection of say 200 trees. These are discrete objects. The space of trees is not, it's sort of this weird uncountable space. Yeah. So it's hard to come up with a notion of a derivative there. So things like
For sure.
HMC or nuts is going to be hard. This is a plain vanilla Gibbs sampler. You're updating trees with kind of a metropolis within Gibbs step. And yeah, I can see the linear leaves in PyMC BART. It's it can be annoying. I fully buy that. But I would say practically, if you wanted to do the Gibbs sampler, it's not going to be too much work. I mean, it's underneath the piecewise constant BART, the standard one.
Yeah.
The real work that's going on is a conditional, like conjugate normal update. So insofar as a linear model, if you put Gaussian priors on those betas or on the slopes, it's still conjugate. It shouldn't be that much more expensive. You might get some thinking about what is the right default prior might be hard. You might try to do something where you look at what variables are split upon in the tree and only use those for the linear predictor, or maybe use all of them. There are a lot of little choices that you need to make that, and to some extent, they're being investigated now. So we're done here, right? So the MCMC is done. It took about 2 minutes to get through about 2,000 iterations with 10,000 data points. So, not the fastest thing in the world, but certainly we're not waiting a week. And so one thing I do want to point out is the output of our chain of our MCMC object, like BART will return many things. It's a list. There's an element for sigma. These are going to be draws of the residual standard deviation. That is, in some sense, the only parameter in the BART model that's identified through the likelihood. So a lot of times when you think about BART, the trees aren't identified. So there's no notion of mixing in tree space that's going to be practically relevant. So what people tend to do when they want to think about mixing is they'll look at the sigma. For every draw of this residual variance or residual standard deviation, you can see, does that do sort of trace plots of that tend to stabilize? If so, your trees have kind of found roughly the same fit. So what we could do is, why don't we look at a trace plot? So let me get my screen set up to do this. I always forget. There we go. So what we can do is, I'm a big fan of base graphics, so here we go. Can you all see that trace plot here on the right-hand side of the screen?
Yes.
Perfect. So what you can see is there is, the sigma started off very large, and then it kind of immediately drops, and then it sort of bounces around a value of 1. And just for reference, there's the true value of sigma, like that in some sense, that's sort of the best one can hope for, right? We know the level of noise in the simulated data set. And it looks like within a few hundred iterations, we certainly have something that would be suggestive of reaching at least a stationary part. If not fully converged, we're at least not changing our fit too drastically iteration to iteration. So if I wanted to be very formal about this, I would run multiple chains. I would look at convergence with like an R hat or like effective sample size by comparing the chains of the sigmas. But in the interest of time, I'm sort of not going to do that. But if you really want to do all of the convergence diagnostics, you can take these and then feed them into Coda or like Bayes plot or your favorite MCMC convergence things. I will say the BART like a lot of the BART packages don't do that built-in diagnostics for you. You kind of have to do it by hand. One of the other things that shows up is you'll get something called yhat.train.mean. These are posterior means of the regression function evaluated the training data. There's the yhat test mean for the posterior mean evaluations on the testing data. Then you also have access to the full MCMC samples. So if we look at the dimensions of say yhat.train, this is this will be 1,000 by 10,000. So the rows are going to index your MCMC iterations. The columns are going to index your observations in the training data set. So you could then turn this into like an MCMC object in Coda and then do, what is the R hat for each individual, like f of x1 or f of x2. Those are also identified, so you can try to do that. But what I'll hopefully convince you of is, even if you don't do that, you'll still get pretty good answers with like a single chain. So to give you a sense of that, I also computed the RMSE and on both the training and the testing. And let's take a look at what those are.
But so basically, we would get good answers too with just one chain. But these diagnostics you just showed, you need several chains to run them, right?
Oh, of course. You would like this. This is a single chain. I mean, there are notions of our hat diagnostics with a single chain. So this would be like Duduka Vats and Christina Knudsen have some pretty cool things about that. But right, if you wanted an R hat value, you need to run multiple chains. You could maybe do it in parallel. You could do it serially. It's when I'm doing things in practice or for applications, I certainly would. I think here we'd just be spending a lot of time waiting for MCMC to finish.
Yeah, exactly. But so just for people using that in the wild, it would be the same advice we give when you just use a classic Bayesian model where you can use nuts. Use several chains, because otherwise there are a bunch of diagnostics that you cannot use, and so that means your chains could be biased. I mean, your model could be biased, but you cannot be aware of it if you just run one chain.
Absolutely. So this was nice. Let me also pull up the timing. Right. So we got reasonable, like, I don't know, 0.28 on the training data set, 0.36 on the testing data set. For reference, like we were using sigma equals 1. So look, we're doing pretty well, I would say. And what I would notice is that this was like 10,000 data points in about 2 minutes. I'm using an M1 Mac. I don't have anything else running. So this is like a fairly fast machine. But what I will try to convince you of in a second is that although this is good, we can do a hell of a lot better. And that has to do with some tricks in a new implementation of BART. So I've been working on a lot of sort of changes to BART underneath the hood, and I will maybe include a link to where this package lives on GitHub. But it's going to look and feel like a lot like the same, at least for the end user. Underneath this, underneath the hood, there's a lot of changes in how BART deals with categorical inputs, how it deals with continuous inputs, how it does some of the internal calculations for the MCMC. And so what I'm going to do is I'm going to rerun the exact same data using a slightly different implementation. And you'll notice that the API is very similar. Here I'm not specifying the number of parameters, like number of iterations, because the default is 1,000 burn-in and 1,000 post-burn-in. So I don't need to specify it. But it would look almost identical to what's in WBART. And as you tell me the Y's, you tell me your training X's, and you tell me your testing X's. The one difference is that the argument now has a slightly different name, because we're going to treat continuous and categorical predictors slightly differently, and we'll pass them separately. So it's not going to be one big data frame. You have to do a little bit of work, but I'll stipulate this could eventually, we could write kind of a pre-processing thing to parse this out. It's just not high on our priority list. If you have continuous and categorical predictors, we'll presume that you know which are which, and you can separate them. So we're gonna let this thing run. So let's keep in mind this sort of 2-minute benchmark and see how we do. So again, 10,000 data points, and we'll let this go. And to address the thing in the chat, like, I think automatic diagnostics is totally cool.
Yeah, Yeah, so apparently that's coming. There's that pull request in PyMC BART. So for sure that'd be cool. Because then afterwards you can probably use RVs again as you do in a classic
Exactly.
pattern,
Yeah.
in a classic Bayesian model, which would be cool for sure. And like so and here, so to be clear, you're using another package to do the same
Yep.
model, and then
Exact same model.
you can compare both models, for
Yeah.
instance.
Yep. And so we should get roughly the same RMSEs. We're not changing anything. There are some subtle like differences in kind of like one's hyperparameter is slightly different. There's how we're picking our cutting points are slightly different. So you should not expect these to give exactly the same answers. They should be close in subsets. And what we'll do is I'll just pull up the names just so you can see it really does look a lot like that. You've got your y-hat train mean, your y-hat train, the same kind of posterior means of the function evaluation on training and testing. You still have a sigma. There is an object to actually save the trees. So this package will do serialization of the trees so that you can then take your fit and pass it to a predict. The BART package does this as well. But we have we sort of serialize in slightly different ways. The trees here are going to be, so what we'll do is we'll look at, just to convince you that the fits are basically the same. Let's see if I've got my plot. No, so I will pull up. That's with our new implementation. It looks almost identical. The sigma is dropping suddenly and bouncing around the true value. And if I look at my RMSEs, they should be similar. It's a little bit worse, but we're talking, I don't know, like 100th of a decimal point. That's like on the order of square root of n. So we're not like that. That's certainly within kind of sampling variability. The testing is very similar. We differ by, I guess, 1,000th of a decimal point, and really the key is the timing. It's 3 times faster, and that has to do with how we're doing the MCMC and some of the intermediate calculations. So that's kind of the first case study to motivate this thing. So let me quickly close this screen and open up a different one. Yes. The best strategy to handle categorical variables. Great question. It leads perfectly into the next case study.
Yeah, so just for people watching the recording and who don't have access to the chat, so the question is, what is the best strategy in your experience to handle categorical variables? Is that one-hot encoding? Because Juan is asking that because when he has many categorical variables, he has used target encoders, quantiles, for example, but he does not have intuition which would be a best choice. And he's saying that the question was not prepared so that it would fit perfectly into the webinar.
No, my answer is neither. There's nothing about trees that suggests you must split on like axis aligned predictors. That is essentially a choice people make for convenience. It's easy to code up, but there's nothing inherent to trees. They are just devices to partition your data set. And on that view, if you have a categorical predictor, there's nothing that says send 2 levels of the category to the left of a decision node and 5 to the right. So what I mean is that you should directly partition that discrete set. And so what this implementation that I've been showing you is all about is doing that. So if you have a categorical variable that has 100 levels, instead of one-hot encoding it or target encoding it, it will just say the tree will be able to split directly on those levels. It will choose a subset and assign it to the left, and it will choose another subset and assign them to the right every time you're doing these sort of splits. And so as a way to motivate this, I'm going to share my screen again, and let's see if I get, yes. So you should now see a new RStudio window. And this is going to be an example from a couple of papers on baseball. So just to set the stage, in baseball, there'll be a batter, and a pitcher will throw the baseball at them, and the batter gets to decide whether they swing or not. So if they swing, they might hit the ball and put it in play, and they start running, or they might get out. But if they choose not to swing at the ball, the pitch is required to be classified as a ball or a strike. And there's a rule in baseball that says these decisions should be deterministic based on kind of the location of the ball. But that's rarely enforced in practice. That in fact, ball strike decisions are extremely noisy. They're made by an umpire. And there's a lot of literature that suggests that umpires can be influenced by the players involved, that certain players may exert influence on the probability of a called strike. And so what we're going to try to do is we're going to try to use BART to learn this called strike probability function. And it's going to be, we're going to take data from the Major League Baseball seasons. And what we're going to do is we're going to have for every called ball or called strike, we're going to have a couple of predictors. We're going to have the location. So it's sort of this the ball is passing in 3 dimensions, but we're going to look at the sort of the horizontal and vertical coordinate of the ball as it passes by a particular point. So it's as it crosses the front edge of home plate, it's kind of a 2D location. And then we're going to have the identity of the batter. We're going to have the identity of the pitcher, the identity of the catcher, and the identity of the umpire. So we've got kind of 6 predictors: horizontal and vertical location, the 4 people involved. Now, obviously, those 4 people are categorical. And to give you a sense, there's about 300,000 called pitches in every year, maybe 350,000. There's about 1,000 batters, 1,000 umpires, about 700 catchers, and about 100 catchers and 700 pitchers. So there's a lot of categorical levels here. So we're going to see that we don't actually need to do any of this encoding to get reasonably accurate results. So what I'm going to do is I'm just going to set up the data. So I've pulled out data for one season, and we need to pre-process it. So there's a couple of things to do in the pre-processing. So I'll just pull it up here, and maybe I'll zoom out. Can you still see this code?
Yes.
Okay. So what we'll do is we'll restrict our attention to kind of regular season games, not the playoffs, not exhibitions, not kind of weird spring games. And then we're just going to select a couple of things. This data frame actually has like 100 different variables. The ones we care about is the description, which is just going to be ball or strike. We're going to ask for the batter, the pitcher, the catcher, the umpire, and the location. So if I quickly just pull up this and plug it into my console, just to give you a sense of what this data looks like. This is what the data looks like. So this is ball or called strike. And each of the players is given like a integer or numeric ID. This is assigned by Major League Baseball. There's a lookup table somewhere that you could actually go figure out who this is. But for our modeling purposes, it's enough that there is an ID. So in our modeling, we want to be very careful when we pass these data to BART. We don't pass this as like a continuous predictor, right? There is just a label. So you'll see that there is an X and a Z coordinate. X is the sort of horizontal and Z is the vertical. And we're basically going to try to predict the label using all of these features. And we've got like 300,000 of them. So we're not going to run the full 300,000. That would take like 45 minutes. And what we'll do is we'll do a little bit of data pre-processing, converting the batter IDs to factors. Just my own kind of personal preference is to prepend a prefix, just so that I never end up adding something to the batters. And then this new BART package, this FlexBART package, it allows you to work with these sort of multi-level categorical predictors, but it requires you to convert them to integers, like not negative integers. And this is a model, this is a like implementation choice. I will argue it is not a particularly tricky one, and eventually we might do some pre-processing to make this easier for users. But for now, all we're going to do is take a factor variable and convert it to an integer, and we'll zero index it. So you can think about the 0 being the reference label. So all we're doing is turning this number into a non-negative integer that starts at 0 and counts up to the number of unique pitchers. So this is a fairly innocuous transformation of the data. It's just there. The other thing we'll do is a lot of BART implementations under the hood scale the x's, continuous x's down either to 0, 1 or -1, 1. I think we use -1, 1 for no real reason other than it's nice and symmetric. So we're going to do that. We're going to rescale these x and z values to -1, 1, and we'll just do that linearly. How you rescale it doesn't much matter for trees. What matters is the order. So even if you're not preserving distance, so long as you preserve order, trees are kind of invariant to that. So we're just going to quickly do this pre-processing. And because it'll take close to an hour to do the whole thing, I'm just going to pull out 10,000 observations, and then for training, and then we'll do some predictions on a further 1,000. So I'll do that. Could just kind of set up a training and testing split. Nothing very exciting. And at this point, we need to kind of just massage our data into a form that is passable to our BART function. And so what we need to do is we have to pull out the outcome and make it an integer, either 0, 1. We need to pull out a matrix of continuous predictors, and we need to pull out a matrix of categorical predictors. And so we're going to do it in sort of a standard way. We've got a matrix of continuous predictors on our training observations, and I'm just pulling down the right columns out of a tibble. There's probably a nicer way to do this in like a fully tidy fashion, but you know, I whatever works in its sort of developer time counts for something. The more important thing is the categorical predictors. So what we're going to do is we are going to put our categorical predictors, we're going to dump them into a matrix. We've got 4. We've got the batter, the catcher, the pitcher, and the umpire. So we just need a matrix of 4 columns, and it's just going to record that integer that we've recoded all of these things as. So it's, you know, we're not creating a one-hot encoding. It is just an integer matrix that records the level. And so we do that for training, and we can do the same thing for testing. And so we're almost done. We've got our y's, we've got our x's for both training and testing. Before we can run this, we need to put in one more ingredient. And that is, we have to tell our BART implementation what are the available values of the categorical predictor. It needs to know basically how many categories there are and what are the specific labels of the categories, right? They're non-negative integers. What we do is we have an argument in our function that says sort of a list of the categorical levels. And it's got to be as many columns as there are in your categorical predictor design matrix. That should be the number of elements in the list. They're matched if you sort of go order by order. Here's kind of how we constructed it. I computed the number of unique batters, and then in my list I have, you know, an element for batters that goes from 0 to the number of batters -1, and the catcher going from 0 to n catchers -1. Eventually, we might put this into some sort of pre-processing where you just give me a data frame and we can parse it out. Yeah. But I would argue that there's sometimes good reasons not to do that.
And as people can see, data manipulation and making sure the data in the right format is extremely important in any modeling endeavor, and is actually a big chunk of the time we spent our lives on.
And I will say that at least a lot of BART implementations have kind of situated themselves a bit downstream of pre-processing. There's been such an impetus over the last decade or so of just spinning up these models and trying different things, and putting linear models or Gaussian processes in the leaves, or doing BART with different likelihoods, that people haven't really, and because it's all kind of bespoke MCMC for different models, they need different computations. It's not as modular as NUTS or HMC or STAN or Pyro or any of or PyMC. Like that's where a lot of the effort has gone, and not in the can we do the pre-processing and anticipate everybody's unique needs. I would think that that's going to start changing pretty soon. So let's get this up, and here's how we run it. We are going to use a probit version of BART. As a binary outcome. We use a probit to take advantage of a conditionally conjugate data augmentation. This is the Albert and Chib augmentation, if people are familiar. Right, our binary outcome is just the sign of a latent Gaussian, and we kind of specify the BART on that latent Gaussian.
So yeah, can you maybe describe a bit the difference between that implementation, which is probit implementation, versus the one you used just before?
Yeah, it's almost identical, except in the MCMC there's one extra step, and that extra step is sampling a latent Gaussian. That's sort of a posteriori. It is coming from a truncated normal. So for positive cases, it gets a sort of a positively truncated Gaussian. For negative cases, it gets a negatively truncated Gaussian. The mean of that latent Gaussian is our regression function, and it has variance 1. So this like the standard like Gibbs sampling for the probit model. All we're doing is adding that step, and then it's the same kind of Gibbs sampling for BART.
Okay, so and you would use that because you have a different kind of observations?
Yeah, you've got binary observations here. It's either a ball or a strike. It's not continuous.
Yeah, it's similar to logit, for instance.
Exactly, and there could be a logistic. There's a couple of ways to do logistic. You could do the polygamma augmentation. It would have very much the same beats, but polygamma can be slow and at scale. And I would argue we're being so flexible with how we're estimating the regression function that if you estimated it on the probit scale, it's not hard just to convert to the logit scale. I mean, if you're being piecewise constant on BART really is just piecewise constant. If you're piecewise constant on probit scale, you're piecewise constant on the probability scale, you're piecewise constant on the logit scale. So it makes the computations that much easier. And I don't know that there's a lot of things that you're losing. Maybe if your data truly was generated from a logistic model, maybe you're going to lose a little bit, but
yeah, the difference
I'm not sure.
It's minimal.
So I'm going to get this running.
Thanks.
What we're going to do is we're going to, we specify our Ys, and then we specify our X's in two ways. We separately specify our training X continuous X's and our categorical X's. So it's a little bit of extra work, but the payoff is much higher. I don't have the comparison with regular BART prepared, but if you look in the paper or a preprint, when you one-hot encode these things, what ends up happening is the trees will separate categories. So take batters, for instance, and we'll put one batter in one leaf and everybody else in another leaf. And so it'll end up partitioning your space in a kind of remove one at a time. So you never actually partially pool over small levels of categories. So you're not able to kind of smooth or shrink over small groups of categorical levels. And that's a real problem for BART. So we can sort of argue conceptually and demonstrate empirically why directly splitting the levels is preferable than this kind of encoding with many continuous variables, replacing a categorical with a continuous. So that's the argument. So this looks like it ran pretty quickly. I guess just for the sake of
I like the subjective subjective message just above, like that ran pretty quickly.
Oh yeah, that's for a larger version of the R Markdown. So I'm just gonna do a couple of like very basic things. We're estimating probabilities, so maybe one thing I'll highlight is the names of this. What did I call this? I called it fit. So what we have is, in some sense, we don't care about the probit transformed probability. We care about the probability. So what we're modeling is that the probability that y is equal to 1 is the Gaussian CDF evaluated at some f. That f is a function of the locations and then the players and umpires. I don't care about f necessarily. I care about the probability. And so what we get is we have the estimated, or like the posterior mean of the training probabilities, the posterior mean of the testing probabilities. We can get the full samples. We get our trees. We have a few other things. This sort of is-probit is used internally when we have a predict. So we can take the trees that are estimated. We actually have MCMC samples for them. Maybe we could look at one of them. So this is kind of how we represent our trees. This is saying that, this is a tree that doesn't have any children and it has some output. So it's an ASCII representation of the trees, and when we have code to kind of read it in and pull it out, it's a very heavy-handed way of serializing. So this would there's a way of reading this that tells us exactly what is the regression tree, what is the third tree in the first iteration. So we end up reading that in a predict, but once we have our probabilities, we can do our usual things like compute the mean squared error, or the Breyer score, or compute the log loss, or compute the misclassification error. And so we can do this, and we can look at those numbers, right? Like our mean squared error was like 0.05 on training and 0.06 on testing. So that would suggest we're not really overfitting. The log loss was 0.17, 0.19. I mean, if you just plugged in the empirical called strike probabilities, you're doing much worse. So this I would consider like our misclassification is only about 8%. And that seems to be the limit. I really can't get better than that no matter how hard I try. And if you just did the proportion of balls and strikes, everything is a ball, your misclassification is 30%. So we're really doing something here. And I think in previous years, I've done kind of very large hierarchical models of this same data, logistic regression models, borrowing strength across umpires and borrowing strength across players. And that got misclassification errors of about 10 or 12%. So we're still doing better. The non-parametrics really are helping here. That's kind of fine. Where I do want to show a little bit of additional functionality is that up until very recently, one big problem with BART, most implementations was you had to specify your testing data at training time. There was not a really good way of taking the tree samples and moving them to a different R instance and then reading them in as to like a predict. So like, how do we generate predictions with new data? In recent years, people have started coming up with serialization of the trees that get to be read and updated. And so we now have access to predict routines. So we had to write them ourselves. It's not like predict.lm or predict.glm, but you can take fitted BART, like objects from like fitted BART models, and pass them to a predict. And so what we're going to do is we're going to specify a batter, a catcher, a pitcher, and an umpire. And then we're going to make a heat map of the called strike probability that's been fitted from our BART model for every location. So we'll lay down a grid of locations and we'll make a prediction at each point for this combination of players. And so that'll just show off the predict. So what I'll do is I'll pick the batter, the catcher, the pitcher, and the umpire, and then I'll lay down a grid. I'll lay down a grid in the horizontal direction. I'll lay down a grid of points in the vertical direction, and I'll look at the expanded grid. So here it's a grid of 0.05 inches. So this is, 0.05 feet. So that's, I don't know, about a half inch, just a bit under or just a bit over. So I'll set that up, and for each point I will create a matrix I'll create a design matrix for this sort of new data. I have to do a new data version of my continuous predictors. I have to do it for my categorical predictors. So if you have used like LM or GLM, it's just like passing your new data. It has to kind of match the format of what you specified at train time. So if you use like predict.glm, you have to specify you have to have a data frame that has all of the variables in your model. It's a lot of the same logic. Some of this code is mostly bookkeeping. Just to create a matrix of continuous predictors for our grid of locations, a matrix of categorical predictors, and then we'll pass it into our predict, and it looks like most predict functions, right? You give it a fitted function or the output of a model fitted procedure. You give it your new data, in this case the new continuous variables, the new categorical variables, and we'll add some print statements. So it's going to go iteration to iteration. it will evaluate each tree ensemble for every point supplied, and it'll output a matrix of posterior samples. So in this case, because it's a probit, I want the probability at each location, and I want all of the samples. So that's what this thing is going to do. And it takes a little bit of time. It's honestly, the predict is the slowest part. The actual training is much faster. And the reason is that here we're taking every observation in our new data set and dropping it down the tree to evaluate the tree. In our MCMC, we're taking advantage of a lot of tricks to not do that repeated evaluation of the trees. That's how we got that 3x speed up that we saw previously. So the dimensions of this guy are 1,000 by 9801. So 9801, I guess, is the number of grid points that we're looking at, and we got 1,000 MCMC draws. So it's just a matrix. You can again turn this into an MCMC object, do your favorite diagnostics. If you want to have multiple chains, you could pass multiple chains and just sort of stack the predictions on top of one another or interleave them. It's exactly what you would do, but we're leaving that to the user as opposed to doing it for them.
Yeah, you should do that.
Well,
and almost 10K grid points. Is that a lot in your experience? Is that actually something you're trying to optimize and get to a very as low a number as possible, or is it something?
No. So this is right. So I chose this grid point because this particular application lends itself to nice visualization. So what I would like is a visualization of that XZ space, where at each point in that space I color it with what is the fitted probability of a called strike. And so all I've done is I've gone to a very fine grid to try to do that. You could go finer, you could go coarser, but what I'm going to do is I'm going to make a heat map. So what I'll first do is compute this is the rows are indexing my MCMC samples. So if I wanted something like the posterior mean, I would need to get the column means. And then what I'm going to do is I'm going to go to every point and I'm going to draw a little rectangle and color it according to that fitted probability. So this is my way of doing a heat map. There are better ways, but again, as a base graphics type of person, this is sort of my preference, my sort of preferred way, and we get a very nice looking heat map like this. And maybe I'll mess around with the aspect ratio so it looks a little bit more realistic. Actually, that's about as good as we can do, and it looks fairly symmetric, but in fact it actually isn't. But the asymmetry is very subtle. So this would say, dark red is sort of 100% probability of a called strike, dark blue is a 0%, and if you're familiar with baseball, the actual rule book strike zone passes kind of in this white region. It's a rectangle that's in there. So we could change the batter, we could change the umpire, and we'd see subtle shifts in this picture. But this was the reason for laying down that grid, was to be able to make a heat map. So this is, again, not something that is provided as part of the package because it is so specific to this particular application. But it could basically say, if you can give me your MCMC samples, we trust that you can make the visualization or the summarization however you like. So I'm going to stop sharing this and pause here if there are any questions or...
Yeah, any questions here, guys? I can see Raul is appreciating your presentation, Samir.
Cool.
So I don't see any pending questions in the chat. I do have a lot of them. So
okay.
Before you go on with the rest, I mean, I don't want to derail your presentation, but I was curious about two main things. One is, it reminds me a bit of splines or Fourier decompositions, where basically the art is trying to decipher how many splines, how many knots you need for your splines, how many Fourier decompositions you need. So here I'm wondering if you have to choose the number of trees or number of leaves, and also how that relates to overfitting. How do you handle overfitting
Great question.
in BARTs? And related to that, what about hierarchical BART? Would that work, and how would that work?
Yeah, basically the number of trees is a super important parameter. What people have found over the early years of BART was you can pick a default value like 50 or 100 or 200 and get pretty good predictive results and reasonably well calibrated uncertainties. You could then try to optimize it with cross-validation. It's a tuning parameter in some sense. And often that requires a lot more compute and not that much more benefit. You can try to learn the number of trees. There's some work that does kind of like very nice reversible jump MCMC. Again, a ton of compute, but you're not getting like 10x or 20x improvement. You're getting very marginal returns. To prevent overfitting, there's in the BART prior specification, each tree outputs a Gaussian. That Gaussian needs to have a prior mean and a prior variance. That mean is usually set to 0. That variance is scaled by 1 over the number of trees. And the reason for that is that if you're adding up capital M trees and all of them have a variance that scales as 1 over M, the total sum has a variance that is invariant to the number of trees. So the same amount of overall shrinkage is being applied whether you use 200 trees or 1,000 trees. In my experience, I've found that 50 often is enough, but I don't know. Now, this second question about structure to the categories is exactly where I'm going next. So what we have in our implementation is we've built our implementation to pull multiple categories to both the left and the right. We've done it in a very naive fashion. We are saying draw some probability with, uniformly. With that probability, send things to the right, and with residual probability, send things to the left. This is fine for things like batters or when you really have no structure to the categories. When you have structure, now we have to do something else. And so one of the big things with this implementation is that we've written it in a way that it makes it extensible. That if you want to build in more structure or more elaborate decision rules, there's a way to do that that is abstracted away from the core MCMC. So don't spend your effort rebuilding the backfitting MCMC, re-deriving the marginal likelihoods, the Markov-Hastings, Metropolis-Hastings transition probabilities. Focus on designing new kind of like splitting procedures, and then you can get just get everything else to run. So that's been a big part of what this software is all about. And I'll illustrate this with an example with networks. So it's not exactly going to be hierarchically structured, but it's going to be network structured. And the idea is that the categorical variable here is the vertex, like the label of the vertex. And maybe that network is telling me, which things do I want to keep together? BART is all about partitioning your data. Maybe there's some levels that you want to partition together. In the case of a hierarchical structure, you can visualize that as a specific type of network, and we can talk about how to do that. But the ultimate idea is that it can be done, but you do need to do a bit of coding and dropping down to C to if you really want this. But we're hopefully going to make that easy. So here is the last example.
Cool. Let's go. Wait,
so
I think I have some drum roll media here. Let's see.
Oh no. What we're going to do is, let me see. Did I do everything right? Yes, I've got everything that I need. I'm going to set. In the interest of time, I won't share all of the gory details. But the idea is that I've got a network, and I'm going to generate observations on the network. That is, at every vertex, I'm going to generate a bunch of XY pairs. I'm going to do it in a way where the regression relationship varies smoothly over the network. The specific way that I'm doing it is I'm picking 2 clusters of vertices. I'm defining a function for all of the vertices in those 2 clusters, and then everything else is going to be a smooth interpolant of that function. So it'll be kind of a weighted average of the 2 functions. The weights are based on some notion of graph distance. I will set this up, and then I will visualize it so that we can kind of see what's going on. Oh, this is in fact not what I wanted. Let me change this. Sorry, can you still see my screen?
Yes.
Okay, great. I loaded the wrong data. But here is, like, here's our network. So the idea is that I've got something like 60-ish, I've got like 60-ish vertices, and there's like some structure to them. So maybe I would like to train a BART model that takes in the vertex label, but I want to make sure that observations from like category 19 tend to be partitioned very close to observations from category 4 or category 20, but maybe not putting 19 and say 61 together. So the network is somehow telling me some of these categories are more similar to others than to the rest. And I would like my trees to be able to split my categories in a way that's informed by this network. And there's a way of doing this. It involves constructing random partitions of networks into contiguous components. There's sort of multiple ways to do this. We have an algorithm we like, but the idea is that I'm going to draw a bunch of data, and I will create some weights on my network. So here's a weighted graph. Let me zoom out a little bit. Can you all see this weighted graph here? I don't know if the colors are showing up. Maybe not. Maybe I can zoom in. Oh, no, let me zoom in here.
Yeah, if you can zoom in, but the colors are, we can see the colors. Yeah.
So the idea is that here in these dark blue nodes, I'm going to generate a bunch of XY pairs where the Ys are noisy observations of some function evaluated at those X's. And then at these dark red nodes, I'm going to do the same thing with a different function. And everywhere in between, I'm going to kind of use Ys are generated as a weighted combination of these functions. So you can think about what I've done is I've got a function that knows the label of the vertex, like the category, and some X's, and it smoothly interpolates from one function to another. And the two functions that I'm going to use are ones that BART can actually learn quite well. So the first is a function of two variables alone. Let me redraw it. It's a function of two variables. It has this sort of downward facing shape if one of the coordinates is less than 0, and it's this upward facing shape if the coordinate is bigger than 0. And then this is your classical piecewise smooth function. Both of these are things that BART actually can learn very, very efficiently. So what will happen is in those blue nodes, the functional relationship looks like what's here on the left. On the red nodes, it's what's here on the right. And everywhere in the middle is kind of a weighted average of these two functions. So we'll generate like 200 observations at each of the nodes. And we've got a continuous predictor, that's our X's. We've got a categorical predictor, that is our label, our category label. We'll make that an integer. The X's will be rescaled to -1, 1. I'll generate all of my data. And what I'll do is we've got about 70-ish nodes. What I'll end up doing is I will pick about 10% of my nodes and designate them as sort of my out of sample nodes. I'm going to hold them out. So when I train, I will train on the full data from like 90% of my vertices. And I'd like to be able to see how well do I estimate this function at new X's at nodes that I haven't seen in training, or in categories that I have seen in training. So it's this kind of infilling problem. I'm not changing the adjacency structure. I'm not changing the network. I am just saying I'm not going to serve any data from a particular category. So it's like, how do we make a prediction about a new category that we haven't yet seen, but we know it exists, we just don't have any data for it. And so intuitively, it's got to be some sort of smooth average of all of the nodes around it, but we don't want to impose that in some sort of like spatial random effect or some sort of graph structured random effect. We want to let these trees learn how to do that by partitioning the node labels in sort of an adaptive fashion. So I know I'm rushing through this. This will all be up on my GitHub, and what we'll do is we'll create 500 test set observations at every node. So in the nodes that we see in training, or the vertices we see in training, This is like, how well can I just learn this function at new x's, given that I've already seen evaluations of that same function at existing x's? And then the real kicker is, how well can I predict this function at the nodes for which we didn't have any data during training? How well are we doing at this infilling task? And so we're going to look at the average over, say, like 500 observations. So just to give you a sense, this is our, the colors aren't showing up here. Oh, that's why. So the idea is that I'm going to see data at all of these gray nodes. I'm not going to see data at these yellow nodes during training. And then I'm going to ask, how well can I predict the function at this yellow node? And how well can I predict the function at the gray node at new x's? So it's sort of two test set cases that we're concerned with. Now, I'm just so that I'm going to compare this with regular BART, which can't leverage the adjacency structure. Regular BART does this one-hot encoding. And so this example should show us the pitfalls of that one-hot encoding. We know a priori that one-hot encoding loses the network structure. We can't expect it to do well, and we'll see just how badly it does. So we're going to run our code. And to do this, we used a specific function for network structured categorical predictors. It's called network BART. It says, give me your y's. Tell me the vertex label. That's kind of which observation came from which vertex in the network. Tell me the training predictors. Tell me the testing predictors. And then give me the adjacency matrix. It's fairly lightweight. It really doesn't require you to pre-specify any functional forms, do anything, just pass the data. And as you say, Alex, pass it in the way that the underlying code anticipates. We're trying to make this as easy as possible. I'm open to suggestions. If people have ideas of like making this easier, this was the easiest that I could come up with. So, okay, we're almost halfway done with this. It's slow. The reason for it being slow is, well, at each step, we're partitioning the network. The way we're doing that is by running a random walk on the network, and on the basis of that random walk, that gives us a spanning tree, and we're deleting the spanning tree. So these are all kind of cubic in the size of the network. So it does get slow, but I think the slowness is worth it if you really want good performance. And to give you a sense, we've got 12,000 observations in training and 34,000 in testing. So these aren't small data sets in any stretch of the imagination, but we're going to be done here in about 45 seconds. So I don't know, that took what, like 2 minutes? Sorry, Alex, I think you're muted.
Yes, sorry, that's better. Yeah, it had to happen, right? That's one of like the good win point of any webinar is someone talking while being mute.
No worries.
Yeah, I mean, 2 minutes for such models and the quantity of data is really impressive. And also, any model is kind of a trade-off of sampling time, but also what do you get at the end? Right? If what you get afterwards is incredible results with uncertainty estimation on everything that matters to you, I would say that's worth waiting 2 minutes of your life. It's not even the time to make an espresso.
So what we're doing here is we're running BART, like plain vanilla WBART. This is out of the BART package. It doesn't deal with these categorical predictors in the same way.
Okay.
It does. It's one-hot encoding them. And to answer the question, what is a great data set for a total novice to try running WBART with? Great question. The best example is the Friedman function, and it's in the examples of the BART package. If you want like a real data application, if you look at the original BART paper, what they did was they did a giant bake-off using a bunch of UCI data sets, right? Like, I mean, we think these are overanalyzed, but as just sort of didactic things, take your favorite data set off of UCI and just try pushing it through BART. A lot of it will be massaging it into a data frame or a matrix that can be passed to the WBART function, and then just going like WBART, your Y, your X, and letting it run. There's really not much else to it. So it looks like, in fact, this W BART here is going quite slowly. It's really struggling. Um, it's not going to get us good fits, and we had to wait a long time for it. So that's you know that's
Yeah,
good
that's
for
cool.
me.
I think that's cool because then you're gonna compare that to another package.
Mhm.
I'm guessing so.
Yep.
It's gonna be
Yep.
cool to see really the difference and on the same model with like just same
The only things that the
parameterization, and it's gonna
only
come
thing
from
that we've
the
changed
algorithm. Yeah,
is so
exactly.
the comparison here is it's the same underlying stochastic model, sort of. The difference is how we're dealing with those categorical things. In one implementation, we're taking advantage of the structure that's been specified by the network, and that has its own overhead. We've coupled that with some additional kind of tricks to get some speed up, and we're comparing it to the original BART model that doesn't have this structure and that is slow at scale because it has a couple of like redundant calculations under the hood. So here I'm just computing the RMSEs. I'm computing the uncertainty interval coverages. I generated my data. I know the answers. So I'm going to ask, I generated 2,000 samples. I threw out the first half. I'm just going to treat them as if they were truly like posterior samples. I've not checked the mixing. I should run more chains, but let's just see how we do with one chain. Let's just see what it looks like.
Yeah.
So it's going to take a little bit of time to compute the coverage because we've got to like loop over all of the data and check individual ones. In the meantime, this question in the chat, would variational inference be an option? No. I'm going to go out and say no because it's this crazy discrete space. If you've got, so maybe there is a variational approximation that's available under here, but to pull that off, you would need to do optimization over the space of trees. I don't think that there is a nice way to embed trees into like a mean field like Gaussian or like mean field Gaussian on a transform scale. And then sort of there's like not even a good notion of a gradient here. We're really discrete. So maybe, but I'm skeptical.
Yeah, and to make it clear to people watching the recording, the question from Juan was to scale these up, to scale the sampling time up, could stochastic variational inference be an option? Samir just answered.
Let me see. Let's look at these results. So here we are. So what we're looking at here is RMSE on training data. So our model that accounts for the network information that really tries to borrow strength or partially pool across the network is across the board better than one hot encoding with BART. It has like 3x better on the testing data set in terms of RMSE. We see that the coverages are okay. These are 95% credible intervals. Any credible interval, there's no guarantee that it has frequentist coverage until like some sort of Bernstein Mises is kicked in. So we should always calibrate our expectations accordingly. I would argue that like 80+% is okay. It's not the best, but for a thing that isn't even supposed to have nominal frequentist coverage, I think it's passable. Maybe in practice, if I really wanted to get like true like frequentist coverage, I would increase the number of iterations. I would run more chains and sort of I would buy coverage at the expense of compute. But as like a quick and dirty like 2-minute thing, I'm happy with 80%. The 50% or the 20% that the one hot encoded BART is getting, that's so low because the intervals are in the wrong place. It's biased. And then in terms of time, one hot encoding using BART, it took like 3-ish minutes. Using our implementation, it took just under 2, and that's with a very heavy simulation to partition your graph. So at scale, we can get this to work faster. The bottlenecks, if we wanted to do this on like the Facebook graph, is generating the splits of the network, and that's something that my group is like working on actively right now, is speeding that up. So in our implementation, we've tried to reduce the as much redundant and unnecessary calculation as possible, but there's still a long ways to go. If you're a user of the BARTs package, this is Vince Doria's stuff. His is even faster because it uses some very cool compiler tricks. We haven't gotten to that part yet, but it doesn't deal with categorical features in a way that I find satisfactory, so I tend not to use it. And I know I've gone well over my time, so I'll stop here.
That's super cool. Yeah, thanks for taking that time, Samir. That's quite clear to me. Yeah, because I never really seen an end-to-end analysis like that with BART. So that's really cool. I mean, really made me want to try this in my own analysis one of these days, and just take that as an excuse to learn up and read about BART. So yeah, thanks a lot.
Absolutely.
Any other questions, folks? Last question for Samir, and actually Juan is asking a question. So, what if you project a network on a Euclidean space, preserving local distances, and pass it to classical BART? So that means we encode the distance in the pre-processing, and don't be sorry, Juan.
Yeah,
it's a detailed question. That's awesome.
It's a great question. It's one that we get a lot, actually. So, right, this idea of like take your network, pick your favorite embedding, and then just pass those embedded features to your favorite flexible machine learning model. This is not a bad idea. Yeah, I guess we could try it. I think where I get worried is that what is the right embedding that you can use? Like you can do a spectral embedding, but like how many of your eigenvectors do you do? What is the dimension? Does it matter? It's in this particular case, do we care about local distances? I mean, these are all questions. I'm not doubting the utility of this. It probably will work very well, but we're introducing a couple of degrees of freedom that you could certainly imagine if the data was generated from, say, a particular graphon, and you didn't use exactly that embedding. You did some sort of like random dot product graph or some sort of stochastic block model graph. If you screw up the embedding, how robust will your results be? Not obvious to me. It's certainly something we can try. We have all the tools to do it. This is, in fact, something that my colleagues and I have started to play around with to really try to understand how to do flexible regression on networks. And this would, again, as you say, if you have new nodes that were not available for training, that is definitely one way to do it. I guess the applications I tend to work with, we tend to view the networks as fixed, but there's others where it's not. So how do we really predict at a new network where we see a new adjacency matrix? What I did in the example here was I used the same adjacency matrix. I didn't modify it even though I held data out. So that would be applicable in settings like in, say, like administrative data where you have data for regions and some regions don't report and you'd like to infill on those. You know that they exist, you know where they are, but you know, for other use cases, yeah, it's hard. It's not obvious to me how to do that with a lot of assumptions, but certainly many options.
Nice. Yeah. Thanks a lot. That's super cool. And I'm surprised that you get that question a lot because it's quite a like detailed, precise question. So
I think a lot of it has to do. I think a lot of it has to do. A lot of my colleagues work with networks. So in talking to them about this, like, oh, I can do regression on a network, they said, oh, did you do this idea that Juan has just suggested? And I said, anything but. So we are there. And I guess I will say, at least philosophically, I really think the utility of trees and where a lot of the richness comes derives from this idea that you can recursively partition any space. All you have to be able to do is code it up and check whether you're in that space efficiently. So long as you can do that, you can fit a BART. It's a matter, it turns it into like a software engineering problem, not a statistical problem. And I somehow have this bias towards if we have our data in a particular space, we should work over the actual space, not some extension of the space. One-hot encoding is you're not working over the actual space, you're working on an extended space, and that has some problems. So
yeah, and especially in setting priors. I mean, it's not something we talked about a lot here, but like when you set priors and things like that, it's always harder when you have to do that on standardized data and stuff like that. So yeah. I mean, always no, because there are some cases where it's actually easier when you standardize the data, but most of the time you have to standardize the data to satisfy the sampler instead of the other way around. Yeah. Cool. I think we're gonna call it a show because you've been very generous with your time, Samir. So
thank you for having me.
That's awesome. Thanks a lot for this very first LBS modeling webinar. I'm so glad that we started by that. I think it was awesome. So yeah, as I was saying, the recording will be available. We'll send that your way, folks, and we'll put into the show notes of wherever I'm gonna post that. I don't know yet where I'm gonna post that and so on. There's still a lot of balls in the air. It's the first time I do that, so I have to think about the infrastructure a bit. It's always a bit of a nightmare. But once I figure out where I'm gonna post that, we're gonna post in the show notes Samir's GitHub repo, and especially that repo where he will have everything for you to reproduce these results. It seems like a lot of folks were happy with your presentation, Samir, so that's awesome. Feel free to reach out to me, folks, because there will be other webinars like that. I don't know how frequently I will make them. It's quite a lot of work, but I'm going to try to do them as much as possible. So if you have some topics you're very curious about and would like to see a webinar like that with someone going into the code live, feel free to reach out to me, whether it's a guest recommendation or a topic recommendation, and I will do my best to make that happen. I can already tell you that I am personally working on 2 other webinars, one about model selection and model comparison, because this is an extremely fast-moving science. This is really at the frontiers of Bayesian sets, and so science on this front changes really rapidly, and I notice in my teaching that usually students are quite intimidated and also lost a bit by what are the better practices right now, even though they are very curious about it. So I'm trying to set that up. And I'm also gonna set up, this one is for sure, it's just a question of when, an episode with Ricardo Vieira, a webinar like that with Ricardo Vieira, where we're gonna dive a bit more into how to do out of sampling predictions in PyMC, because these had changed quite a lot since PyMC 3. Now we're on version 5, and the API has changed quite a lot. It's better now, but we need to update people about how to do that, especially for hierarchical models. So I will definitely do that webinar because students are usually lost on that front. Anyways, I'll stop here because you know me, I can talk for 3 hours. Thanks again, everybody, for tuning in. I'm super grateful to all of you. Take care, and we'll see each other in the next webinar. And as I always say, best Bayesian wishes.
Let me show you how to be a good breezy and change your predictions.